Good morning everyone. So in the last class we talked about Kuratowski theorem, which gives us a method to check the planarity of a graph. Today we are first going to talk about Wagner's theorem, which again going to give us a method to check the planarity of a graph. And after that we will introduce the concept of dual graph as well as the crossing number of the graph and how do we compute the crossing number of a graph. So for the Wagner's theorem we need some concepts. So we start with contraction of a graph by an edge. So it's an operation which removes an edge from the graph while merging the two vertices it previously joined. It would be clear with an example. So let us see that this is the graph G and you want to contract edge E. To contract edge E, you replace these two vertices by a single vertex, let's say W. You can give the other name here 3 4 5 and then you have UV. So you replace UV by W and then all the edges which are adjacent to UV must be adjacent to W. So one is adjacent to U, so it must be adjacent to, then 2 is adjacent to V, so it goes there. 1 and 2 itself are adjacent, 2 is adjacent to 4, W is adjacent to 5, W is adjacent to 3 because U is adjacent to 3 and V is adjacent to 5. Other than that, 1 is adjacent to U as well as 1 is adjacent to V. So therefore, there comes the two edges between 1 and W, and this is the contraction of this graph. So if after contraction you make the graph simple, then it is known as the simple contraction. So the same example if you consider and you try to contract, it is the same, not the same example but quite a similar example. You can again call it 1 2 3. So if you contract UV, let's replace it by W. So 1 is adjacent to W, 2 is adjacent to W, but 2 is also adjacent to V and V is adjacent to 3. So if you do not consider the multiple edges, if you keep the graph simple, so 1 2 W and 3, then we call it a simple contraction. So moving further, we say G dash is a contraction of graph G if G dash can be obtained by a sequence of simple contractions. So you can do the contraction multiple times. So for example, if you consider this graph G, take it as an exercise and try to contract all the circled edges. So you can contract this edge, you need to contract these two edges, and you need to contract this one. Again, you can give some numbering if you want, 1 2 3 4 5, then 6, then 7, and then 8. And remember that the contraction should be simple. So if 6 and 7 can be contracted, then 8 would be adjacent to 6, and if you try it by yourself, then it comes out to be a very simple graph which looks like this. It is so because you can see that these two edges would be contracted to a single edge, these two edges again would be contracted, these two vertices are contracted to a single edge, and so on. So in the end there are only 4 vertices, and since we have to keep the contraction simple, therefore we will obtain this graph. So if G dash is a contraction of a subgraph of G, then it is a minor of graph G. Let's see an example. So check if H is a minor of a graph G, which means you need to find, if it is a minor, then you need to find a subgraph of G which if contracted would lead you to graph H. So it's quite simple. The first step is to look for a subgraph of G. So I delete this vertex and then I can delete the 2 more edges. So this is how the subgraph looks like, and then I contract this edge. So when you contract this edge, then it will turn out to be graph H. It means that H is a minor of graph G. We will do many exercises based on the concept of the minor. So let's talk about Wagner's theorem. It says that a graph is planar if and only if it contains neither K5 nor K33 as a graph minor. Yes, in case of Kuratowski theorem, we talked about homeomorphic. In this case, homeomorphic is related to subdivision, minor is related to the contraction. So it means if it has a graph minor as K5 or K33, then it is non-planar, otherwise it is planar. Let's see an example. So if you recall the Peterson graph, then it has a subgraph which is homeomorphic to K33. Yes. So to have this homeomorphic to K33, if you recall, we deleted these two edges, and this is how the graph looks like, which is a subdivision of K33. Now this is interesting, subdivision, because whenever you think of a subdivision, let's say this is an edge and subdivision, so this would always lead to the edge 1 3 if there is a degree 2 vertex. So if you think in terms of the contraction, then how does it behave? So you can do it like this. So these are the vertex 1 2 3 4, then 5, then 6, then 7, and 7 is adjacent to one more vertex, 4 is also adjacent to one more vertex, 6 is also adjacent, and this is how it looks like. But when you try to contract it, you will see that these degree 2 vertex would be merged directly here, so there would be an edge. Similarly, this would be directly adjacent to this one, then this would be adjacent to this one, and then this would be adjacent to this one, and this would directly lead you to K33, because you will have only blue and yellow vertices in the end. So contraction is quite easy. And this is an interesting observation, that if there is a subdivision, then there is a contraction. So K33 as a graph minor by contracting the dotted edges. Now if you recall the Peterson graph, then it does not have a subgraph which is homeomorphic to K5, because it does not have 5 vertices whose degree is 4. Now the question comes that, does Peterson graph has a subgraph which can be contracted to K5, which means does it has graph minor as K5? Please do try it by yourself. And if you observe this, then you need to contract the following edges now. So this edge, these 5 edges, and once you contract them, then what will happen, that because of this contraction, it will be adjacent here, there, 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 and there. Please do try this contraction, because we need a simple contraction. So when you contract this edge, then you can see that these two vertices are adjacent to both, these two vertices are adjacent to white one, so they will be adjacent to the red one. And when you keep contracting the white one, in the end you will have only the red edges, and therefore you will have K5 as graph minor. So it means Peterson graph does not have a subgraph which is homeomorphic to K5, but it has a K5 as a graph minor. So use Wagner's theorem to check if the following graphs are planar. Two simple examples. You need to quickly check them, and then you can see the discussion. So if you see the first one, then you can observe the degrees. This degree is 4, this one is 4, this one is 5, this one is 3, C the degree is 5 and degree of A is 3. Now to have K5 as graph minor, I need 5 vertices of degree 4 or degree at least 4, and G the degree is 4. So already in the center you can see that there are already the vertices whose degree is 4 or more than 4. But at the same time it does not lead you to K5. So what you need to do is that you need to contract some edges. So let's say I want to merge this A with D, because when I merge it, then you can visualize E would be adjacent to D. So this is how it will happen. So if I merge this one, then this is E, F, G, this is D, C, and when I merge the edge AD, then A is adjacent to E. It means E would be adjacent to D. So E would be adjacent to D. Other than that, A is adjacent to C. So E would be adjacent to C, which is already there, and A is adjacent to E. So only this extra edge would be added because we need the simple contraction. Similarly, when you merge the edge FB, then B is adjacent to C, and therefore F would be adjacent to C. And now you can see that each of the vertex is adjacent to all other vertices, and therefore it has K5 as graph minor. Next question. So the similar example we have done in terms of the Kuratowski theorem also, and you can see that it has a subgraph G dash which turns out to be subdivision. It means that if you contract it, then 1 would be adjacent to 5, and that gives you K5. So we deleted the edges 3, 6 and 4, 6, got K5, and which further get contracted to K5. So again from the Wagner's theorem, it is non-planar. So this is a very important observation which says that if G contains a subdivision of G, if G contains a subdivision of H, then for sure H is a minor of G. But the converse is not true, which we have seen in terms of the Peterson graph. So Peterson graph, let G is a Peterson graph and H is K33. So Peterson graph contains a subdivision of K33, which means K33 is a minor of the Peterson graph. But if you see the converse, then the converse of the above lemma is not true, because K5 is a minor of Peterson graph, but the Peterson graph does not contain a subdivision of K5. So whenever there is a subdivision, of course there is a minor, but converse is not true. The next simple concept is the duality. So it says that given a plane graph G, if I have to construct the dual graph G star, so it is again a plane graph where you replace or you represent each face by a vertex, and the correspondence between the edges are as follows. So if an edge lies on the boundary of a face, so let us consider a very simple graph. So if I have to find its dual graph, I represent all the faces by a vertex. So 3 faces are there, and if there is an edge which lies on the boundary of 2 faces, then the endpoints of the dual graph are the vertices xy that represents the faces. So here this is an edge which lies on the boundary of 2 interior faces, so you make them adjacent. Then this is the edge which lies on the boundary of the exterior and the interior face, so you make them adjacent. Then this one, then this one, and then this one. So here you can clearly observe this is the dual graph of the given graph, which again is a planar graph or plane graph. So try this exercise by yourself. So find its dual graph. So dual graph looks like this one. The important observation is this loop because this is an edge which lies on the exterior face only. In other cases, an edge is shared by two different faces, but this is the case where the edge is shared by the same face, and because of which loop is formed. Now consider the following two examples and check if the following graphs are isomorphic. So again, it can be easily observed that yes, it is isomorphic because we have just shifted B to the inside, but when we shifted it, then you can see that the faces get changed. The exterior face on both the graphs are different, and because of which, if you try to draw their dual graphs, they comes out to be different, because dual graph depends on the faces or on the plane drawing. So two isomorphic graphs can have different plane drawing, and therefore they can have different dual graphs. So dual graphs are not isomorphic, and if you try to draw them, this can be easily observed. So the last topic of this chapter is crossing number. So crossing number gives us an idea that how non-planar a graph is. It is denoted by CRG, and it is the minimum number of the crossing in any simple drawing of G. Okay, so let's see some example. If it's clear that if graph is planar, then crossing number must be 0, and for the non-planar graph it should be at least 1. So please do try this exercise by yourself, and you need to find the crossing number for this graph. I am also drawing it. So order is 7, and each one is adjacent to 4 other vertices. I can also number them 1, 2, 3, 4, 5, 6, 7. So to begin with, I can draw the internal edges as much as possible without crossing. If I add one more edge, then crossing would come into the picture. Now after that, let's try to go from outside. So 2 is adjacent to 4. Now degree of 5 is adjacent to 7. So 6 is done, its degree is 4. 1 is done, 2 degree 3, 3 degree 3, 4 is done. So 2, 7 needs to be adjacent, so we can make them adjacent, and after that 3, 6, 3, 5 need to be adjacent. So when you make 3, 5 adjacent, then there comes a crossing, and it means that this to draw this graph, if it is non-planar, then at least one crossing is required. Of course, we have not proved that it is non-planar, that you can do by yourself, but the crossing number comes out to be 1. Let's try one more example, Peterson graph. So try to compute the crossing number of the Peterson graph. If you try it, you will find that it comes out to be 2. But right now we do not know any method to show that why the crossing number is 2. But mathematically, if we are claiming it to be 2, then two things are required. The first thing is you need a drawing with crossing 2. The other thing is that you need to prove that the crossing number cannot be equal to 1. So this is a result which we are going to discuss, which helps us to compute the crossing number, and it says that let G be a graph on n vertices and it has 3n minus 6 plus k edges, then any plane drawing contains at least k crossing. It is because we know that the planar graph has at most 3n minus 6 edges, so more than those edges will lead to the crossing. But there can always be graph, for example Peterson graph, which have less than 3n minus 6 edges but still have the crossings, and this is because the crossing should be at least k. Now we have done many results like this, and it can be easily proved using mathematical induction. You can try it by yourself. I am quickly showing you. So for k is equal to 1, we have 3n minus 5 edges, and which means it has at least one crossing. Now let's say assume that result holds for k, and we need to prove for k plus 1. Now for k, we know that it has at least one crossing, which is denoted by the crossing of edges E and E dash. If I remove this edge E, then after removing it, it gives us a drawing of a graph with 3n minus 6 plus k edges, because you delete one edge and the induction is on k. And for 3n minus 6 plus k edges, by induction it has at least k pair of the crossing. When you put the edge E back, it would have at least k plus 1 crossings. Now let's see how this result is helpful in computing the crossing numbers. So compute the crossing number of k5, k44 and Peterson graph. Now we know that k5 has more than 3n minus 6 edges. So let's say it has 3n minus 6 plus k edges, which means it has at least k crossing. So for k5, the number of the edges are 5 cross 4 by 2, which is 10. And 3n minus 6 is 3 cross 5 minus 6, which is 9. It means k5 has at least one crossing. It means if we can draw k5 with one crossing, then 1 is the crossing number. So this is the drawing of k5 with one crossing, and this is why its crossing number is 1. Now let's move to k4, 4. Please do try it by yourself. The interesting observation is k4, 4. So instead of 3n minus 6, you have to modify the result, and you have to see that it has at least 2n minus 4 plus k crossings. Yes, because the bipartite graph can have at most 2n minus 4 edges. So 2n minus 4, so n is equal to 8. So this comes out to be 8. And 2n minus 4 plus k crossings are there. So it means it has at least, 2n minus 4 instead of 8, 2n minus 4, which is 12. And k44 has 16 edges. It means it has at least 4 crossing. If you can find a drawing, please do try by yourself with 4 crossings, then you can say that the crossing number is 4. So this is the drawing with 4 crossings. Recall that in the bipartite graph it has no odd cycles, and it's a complete bipartite, so all the cycle length is 4. So you need to try to draw it in such a way with cycles of length 4 that it would have 4 crossings. The last one is that we have already seen the Peterson graph. The crossing number is 2, but we haven't proved it. Now it is not a bipartite graph, so 2n minus 4 does not work. 3n minus 6 does not give us the number because it has already less than 3n minus 6 edges. So if you see that, it comes out to be at least 5, 6. It is not coming out to be at least 2 crossings. Now if you recall the tutorial sheet, then the tutorial sheet we say that the graph is planar, then it has at most, we counted it in terms of the girth. So recall that what was the result which we done in terms of the girth. It says that it has at most n minus 2 g by g minus 2 edges. It means it has n minus 2 g by g minus 2 plus k crossings. If you use this result, then we know that n is equal to 10, so 8 cross 5 by 3 plus k. So 40 by 3, 13, and the edges are 15. It means it has at least 2 crossings, and this is why the crossing number of the Peterson graph is 2. So that's all from today's class. In the next class, we will start a new chapter, graph coloring.